This video will walk you through simple regression, which is shown in Chapter 14 of your textbook. Simple regression relates one variable to another in a way that you should be familiar with from algebra, where you use the equation y equals mx plus b, where x and y are your two variables, m is your slope coefficient, and b is your vertical intercept. So have that general idea in mind. I'm going to be referring back to it quite often. Basically what we're going to do is use data to generate that y equals mx plus b relationship, and then we are going to use that equation to test hypotheses and analyze our results. Basic terms involved are independent variable and dependent variable. The independent variables are the variables that are being related to the dependent variable. The dependent variable is the variable being predicted based on its relationship to the independent variables. Yeah, you gotta love these like useless definitions. Okay, so your dependent variable is y, your independent variable is x. So you believe that x predicts y. That's the easiest way to remember it. I believe my independent variables can be used to predict my dependent variable. The regression equation that describes how y is related to x and an error term is called the regression model. So we have three different things written out here. We have our classic example, y equals beta 0 plus beta 1 x plus error. Again, this is basically just y equals mx plus b. So beta 0 is your y-intercept. That was your b term. Beta 1 is your slope coefficient of your line, and e is your error term. So we're going to have this hypothesized relationship, beta 0 plus beta 1 x plus error is equal to y. And we are going to use that information to estimate our y. That's our second equation. Our expected y is equal to beta 0 plus beta 1 x. We won't know the error term. And we're going to actually predict y's using the third equation. So after we've calculated a beta 0 and a beta 1, we can plug in our x's and get our predicted y's. So predicted, when we signify that, that means it has a hat on it, so that third equation is your prediction. Here we see a couple of regression lines, and here again we're just looking at what our slope coefficient tells us. Remember, your slope coefficient was your m. In this case, it's beta 1. So in the first case, we have an upward sloping line where beta 1 is positive. In the second case, we have a downward sloping line where beta 1 is negative. And when beta is 0, meaning that that'll result in a flat line. Now notice we don't just start at the origin 0, 0. We are starting at our beta 0, which is going to be our vertical intercept or our y-intercept. And in the y equals mx plus b terminology, that was b. The estimation process. So how does this work? We have an estimation or a regression model where we believe x is related to y. So we come up with this theoretical y equals beta 0 plus beta 1 x plus some error term. We then write out our regression equation. So we regress x on y using a statistical software, usually Excel, and that will produce these estimates of beta 0 and beta 1. So you'll gather your sample data, you'll run your regression equation, you'll get sample statistics of beta 0 and beta 1, and those estimates, or B0 and B1, and those estimates, or those provide estimates of beta 0 and beta 1. So this is just like the same methodology you've been doing all along. You're using data from a sample to make predictions about the overall population. So technically, when you're using the betas, we're talking about a population, and when we're using the Bs, we're talking about our actual sample. What you'll tend to see in academia is they're used interchangeably. So that can get a little bit frustrating. But again, beta or B, again, we're referring to the same basic idea. So beta 0 or B0 will be your y-intercept. So B0 is your y-intercept using your sample data, and B1 is your slope found using your sample data, and it's used to make a prediction about beta 1, your slope for the overall population. So how does regression actually work? Your goal is to minimize the errors. So your goal is to minimize that E term. So what we're doing here, we see in this first equation, we're minimizing the sum of the square difference between your actual y and your predicted y. And the way that we do that is by finding the appropriate slope coefficient. So actual x minus average x times actual y minus average y, and we're going to divide that by the variance of x. And once we get that beta 1, we already have our x bar and our y bar. That'll allow us to calculate our beta 0. So the goal of all of this is to minimize your errors. So these are the equations that Excel is actually going to perform. We'll go through this twice, once where we do this by hand with a small data set, and then we'll look at it again where we show using Excel. So here's our example. Reed Auto periodically has a special week-long sale. As part of the advertising campaign, Reed runs one or more television commercials during the weekend preceding the sale. Data from a sample of 5 previous sales is shown. It says in the next slide, but I wrote it there. So we have 5 previous sales. We can see our data. The first week the first example, they ran 1 ad that week, and then they sold 14 cars. The second sample, they ran 3 ads that week, and they sold 24 cars, and so on and so forth for 5 total sales and advertising relationships. So the first step there is to get the sum of x and the sum of y, and then the average x and the average y. Next, we calculate the slope coefficient. So the slope coefficient is found by taking the sum of each individual x minus its mean times each individual y minus its mean. So when we do all of that, we come up with 20 divided by the variance of x, which is 4, and we come up with a slope coefficient of 5. Since our mean of our mean of y is 20 and our mean of x is 2, I can plug in that 5 into this equation, y bar minus beta 1 x bar, in order to get my y-intercept of 10. So I come up with a predicted regression equation of y is equal to 10 plus 5x. So how do I interpret this? Y equals 10 plus 5x. So beta 0 is interpreted as the number of cars sold without any TV ads. So it's your value of y when x is 0. It's always going to work that way. Value of beta 0 is value of y when x is 0. Oftentimes, however, 0 is out of the potential data set, so it really has no useful interpretation. In this case, I mean, we're looking at running ads for anywhere between 1 and 3, so 0 isn't so far out of the range that its value is useless. But if you're looking at, significantly larger data values there, then you'd see that beta 0 really has no useful interpretation in those cases. Beta 1 is your slope coefficient. So for each additional TV ad, for each additional x, sales are predicted to increase by beta 1. So beta 1 tells you the expected increase in y for each additional x. So x here are TV ads. For each additional TV ad, sales, which are y, are expected to increase by beta 1, which is 5. We can do this in Excel in 2 ways. One just is a visual, making a scatter plot and a best fit line. So in order to do this, it's really important, put your data in order. First you have to have x, then y. So you have to have your columns arranged in that particular way. Remember, you believe that x predicts y. X is your independent variable and y is your dependent variable. Then you will select that data. In other words, just highlight it. Click the Insert tab, and insert a scatter plot, and then all you need to do is rename your axes. Now notice I selected layout 7. Layout 7 is the one that actually gives you the regression equation there. It also gives you an r squared. So if we follow that methodology using this data set, we will get that same equation, y equals 5x plus 10. So if you sell 0 cars, if you have 0 ads, you're expected to sell 10 cars. Each additional ad is expected to result in the sale of 5 additional cars. We can also use Excel's regression analysis in order to do that. So here it's a little bit different because here you input your y range first and then your x range. So y is dependent variable, x is independent variable. Be really careful about this. This is the most common mistake, is just switching x and y. And I say just, but when it comes to actually, performing the analysis and doing the interpretation, that's a huge deal. So enter your dependent variable first, then your independent variable. Make sure that you check off labels if you have labels in your first rows, and you probably should. Confidence level is 95%. We have this because we're going to be doing hypothesis testing using this data. Make sure not to check constant is 0. What that would do if you had that checked was automatically make your beta 0, 0. You do not want to do that. So make sure you do not check constant is 0. Put your output wherever you want and click OK. So here is the output that Excel will give you. Now, this is quite detailed. Let's talk about what exactly this is giving us. We have information here, R squared, degrees of freedom, SSR, SSE, SST, MSR, MSE, your beta, your p-value of f, a whole bunch of stuff. Okay, first things first, look at your regression equation. How can you find that? That's way down at the bottom where it says intercept and TV ads and the coefficients, okay? So this tells you the coefficient of intercept is 10. So beta 0 is 10. Coefficient of TV ads is 5. So beta 1 is 5. So y equals 10 plus 5 times TV ads. Because x is TV ads, it's better to just put that in. Okay, what else is given on there? R squared is going to measure how good our regression is. We'll talk about that on the next slide. Let's start with MSE. MSE is the standard error of the regression. That is equal to SSE divided by n minus 2. Okay, remember, your goal was to minimize errors, right? So SSE looks at the difference between your actual y and your predicted y. It tells you the variation in y not explained by your regression. So in order to understand this better, it's probably easier if we start by looking at this slide. Okay, so SSE is actual minus predicted. It tells you the variation in y not explained by your regression. So you want to minimize that. SST is actual minus average. SSR is predicted minus average. So it's the variation in y explained by the variation in x. SSR, variation in y explained by the variation in x. So this is kind of looking at how our independent variable relates to our dependent variable. The better that relationship, the smaller our errors will be. So if we go back up here, our goal is to minimize errors. So in effect, we're minimizing MSE, the standard error of regression, because your goal is to minimize the sum of squared errors. Typical. Okay. So SSE shows us the typical amount we miss in estimating each y value, so the typical error amount, and we want that to be as small as possible. So we can continue with this general idea looking at how good our regression is. Well, the quality of our regression is analyzed using the R-squared, which is calculated as SSR, which is predicted minus actual, divided by SST, actual minus average. Now those predicted, actual, average, those are all your Y's. Okay, so R-squared is called the coefficient of determination. It tells you the percentage variation in the dependent variable explained by the regression. In other words, it tells you how good of a job your regression did at explaining the variation in y using x. Now, in multiple regression, you'll be using several x's. In this one, you're just using that one individual x. So if we look at this, our R-squared is 0.87. That tells us that 87.72% of the variation in y, which is cars sold, is explained by our regression. And we can go back and see where we would find that. That's in that initial summary output R-squared. So that tells us how good of a job our regression did. So how good of a job TV ads did at explaining car sales. So TV ads explained approximately 78.72% of car sales. Next, we can look at our significance tests. So to test for a significant regression relationship, we construct a hypothesis test to determine whether or not the value of beta 1 is 0. Remember, beta 1 is your slope coefficient. It tells you how a 1 unit increase in x will impact y. So if there's a statistically significant relationship, this should have a value. Beta 1, B1 should have a value. If its value is 0, then that means that x has no impact on y. So this is going to be one of the most important things that we look at. So our hypothesis, beta 1 equals 0, is HO. Beta 1 is not equal to 0 is HA. So it tests how well the independent variable, and in this case there's only one, does at explaining the dependent variable. Now note there is a slight typo on here. This HA should also say beta 1. Obviously your null and alternative hypothesis do have to test the same thing. So that is an error there, I'm sorry. So HA should say beta 1 is not equal to 0. So the test statistic is MSR divided by MSE. Again, all that information is found in the regression output, but you don't have to do that calculation yourself. Instead, you would just look on Excel at significance of F. So I'll show you that here. Significance of F is 0.0189. It's basically your p-value of your F statistic. So you use the same basic methodology. If your p is low, reject the HO. So it's less than 0.05, so I reject HO. The statistical evidence is sufficient enough to conclude that we have a statistically significant relationship between the number of TV ads aired and the number of cars sold. So another way of interpreting this, I am 95% confident that TV ads do have an impact on car sales. So I am 95, if you reject HO here, I am 95% confident that X impacts Y. We can test this in another way. Again, it's still a significance test, still looking at beta 1. Here we're going to look at the t statistic. So on Excel, we're going to look at the p-value in the regression output box. So the p-value of each individual beta. Now here you only have one. Okay, so at this point you're kind of wondering, well, wait a minute, doesn't this F test and the t test do exactly the same thing? Yes. In the case of a simple regression, this f-test that you just saw and this t-test that we're going to look at now will give you the same results. In multiple regression, which we'll talk about in the next chapter, that's where you have more than one independent variable. In other words, more than one x variable. If that's the case, then you need to perform both the f-test and the t-test. However, in simple regression, you can just look at the f or the t. They're both going to give you the same results because they're both testing the same thing. Now, this is a little odd here because the circle seems to have drifted up. Again, we're looking at the p-value of the x variable. Here your x variable is TV ad, so this p-value that should be highlighted here is 0.0189. So that is less than 0.05, therefore you reject HO, so you're 95% confident that there is a statistically significant relationship between X and Y, in other words, between TV ads and car sales. Confidence interval. You can look at the upper and lower 95% that's reported in your output. And you are 95% confident that each additional x will increase y by between lower 95 and upper 95. So in this case, I'm 95% confident that each additional car sale, which is, that each additional TV ad will increase car sales by between 1.56 and 8.43. All right, so let's just go back to that full Excel output so you could see where you are finding all of this and what we need to focus on right away. So the R squared tells you how good of a job X did in predicting Y. You're also looking at the coefficients, the intercept, and the variable of interest. That's going to give you your regression equation. You also care about the p-values of each of those individual x's to determine whether or not that x has a statistically significant impact on y. We are looking at the upper and lower 95% to get the 95% confidence interval of the impact of x on y. Now note this repeats it twice. It default does 95%. You can change one of those percentiles if you wanted to be 90% confident or something. Otherwise, I usually just go and delete the second upper and lower 95%. And finally, you can look at the significance of f in order to determine whether x has an impact on y. Now, in this case with simple regression, you'll notice that the p-value of f and the p-value of your t-statistic are both the same. Why is that? Because there's only one independent variable in this case. So let's keep going. Okay. Using OLS to make predictions. So what we just did, and when we ran that regression, when we used X to predict Y, that's called OLS, or ordinary least squares. So it's called that because you are minimizing the sum of squared errors of the mean. So least for minimize and then squared errors. Okay, so you would plug in an x into the regression equation and it spits out a y. So you would use this to make individual predictions. So if the company ran 3 TV ads, how many cars would you expect them to sell? So plug in x equals 3 into your equation and you would expect 25 cars. Now obviously this works best when your x is within your data set that's actually observed. If I were to go in and stick in like 504 ads in here, well, if my data only had observations between 1 and 3 ads, then the value that it spits out is pretty much going to be meaningless. So you really want to make sure when you're using OLS to make your predictions that the X inputs that you're using are relatively consistent with the X inputs that you've used in order to estimate that regression equation. Assessing the assumptions of our regression. Okay, so in order for the regression process to work, we have to assume that the error term is a random variable with a mean of 0, that the variance of the error term is the same for all values of x, that the error terms themselves are independent, and that they are normally distributed. So these are our 4 assumptions that we use in order to run OLS, in order to make it work. In a more advanced class, you would go through and we'd show how to assess each of these 4 assumptions and how to make corrections for any violations. The easiest thing that you can do is just to look at the residual output plots. You can check that off in Excel. Just, click plot residuals, and it will show you this here. So assumption 2 says that the variance of the error term is the same for all values of the independent variable. In other words, there is no pattern in your variance of your error terms. There is no pattern in errors. So you should see a random clumping around 0 if that assumption is not violated. If you start to see a cone shape pattern or any other type of pattern taking shape, those are violations of that assumption. And specifically for these 2, there are fixes that can be done. So if you're interested in learning more about that, let me know. I have PowerPoint slides that will show you how to assess the assumptions of regression in Excel and how to go about fixing them as well.